Let's do another CFD report. CFD simulation summary results 4/19/25. Analysis report of a 13.3-inch turbine designed initially for CO2 capture system. This design was additionally designed for an output of greater than 20 to less than 600 horsepower that can handle greater 60 and greater than 2,200 pounds per square inch at gauge and a flow of greater than 3,100 SCFM at CO2 per specifications of the system. Developed that I was requested to design for this turbine for, designed by Brian B. Williams, scientist engineer. CFD prep by Joseph Delavera, aka Flojo, CFD expert. Objective: simulation addresses fluid dynamics and thermal performance within a rotating turbine assembly, analyzing mass flow rates, torque, and velocity streamlines to evaluate operational efficiencies and identify fluid behavior within the geometry of the specifications stated above. Key matrix from simulation: outlet MFR, mass flow rate, kilograms per second, minus 2.077, average minus 2.07703, minimum minus 2.07985, max minus 2.07514, delta 0.00043, inlet MFR, mass flow rate, kilograms per second, 2.087 unit value, average 2.08559, minimum 2.08144, maximum 2.08930, delta 0.00060, torque TZ, foot-pounds of torque, 22.08, unit value, average 22.13, minimum 21.69, maximum 22.61, delta 0.15764. Performance implications. The simulation reflects well-defined fluid behavior and mechanical response, with clean mass balance and rotational work extraction via torque, which clearly matches the closely related 12-inch turbine's physical output characteristics. Internal vortices are important as they aid in energy exchange and extraction. The small deltas in data and validate the robustness of the simulation, confirming that further post-processing, thermal gradients, stress fields can proceed with confidence. Key observations: mass flow rates above the inlets and outlets are well matched, indicating near steady flow with negligible loss or accumulation, which validates the conservation of mass. The small delta values across all goals reflect stable convergence within this CFD complex, or complexity of the CFD solution. Net torque, TZ, around the central z-axis is positive and consistent, suggesting effective momentum transfer from the fluid to the rotor assembly and vice versa. This brief spike near iteration 300 is more likely due to changing boundary influence, which is normal in this type of CFD analysis. Final torque values are consistent, supporting mechanical efficiency and energy transfer consistency. Again, validated in physical and empirical testing of similar units. This simulated system achieved a final thermal to mechanical efficiency of approximately 42.5%, which is an impressive result, especially when benchmarked against comparable energy conversion technologies of similar size and power class. But again, I have backed this up with empirical testing of similar size units. Below is a chart of total entropy in versus out across iterations. The red line, total entropy entering the system, orange line, total entropy leaving the system. The clear drop from the output to, or from input to output represents the thermal energy that is converted into mechanical work. You can't see the graph, but it's there. And it shows a red line and an orange line. And they show the total entropy versus out. Flow direction convection. Most CFD solvers like SolidWorks, ANSYS, ANSYS, Fluent, etc. use a sign convection. The positive enthalpy flow means energy is leaving domain, i.e. outflow. Negative enthalpy flow means energy is entering the domain, i.e. inflow. In this case, the inlet enthalpy rate is negative, meaning heat energy is entering the system via the inlet mass flow as expected. The outlet enthalpy rate is positive, meaning heat energy is leaving the system through the outlet, again to be expected. This is normal and correct. It simply follows the sign conventions used by the solver. Flow temperature and pressure profile from the image above, real up. You can't see the chart, but it shows a temperature across the system from minus 500, minus 25,000 F to 600 F drop in temperature. Fluid enters at high absolute pressure and velocity. Vortical zones suggest strong internal mixing, aiding in energy extraction, but also indicating possible localized heating and thermal gradients. Internal zones likely generate compressive heating and stagnation points and expansion cooling near outlet. Thermal performance, metrics, inlet mass flow rate, estimate observation, around or approximately 2.087 kilograms per second. Mechanical output, power output, approximately 9.4 kilowatts. Estimated thermal power in, 22.1 kilowatts. Thermal to mechanical efficiency, 42.5%. Likely losses, friction, heat to wall flow separation. Flow dynamics, strong swirl, localized recirculation, directional flow at outlet. In comparison, a typical single-stage rotor blade turbine operated under similar conditions with low to mid-range enthalpy input and compact flow factor generally achieves efficiencies in the range of 30 to 33%, with much higher requirement for flow and pressure. This design in this simulation notably outperformed that baseline, demonstrating superior fluid handling, torque generation, and internal flow optimization. Note that this simulation is backed up with video of similar process under slightly modified, which can be replicated in conditions that have the same results. When set against a Stirling engine of equivalent scale, well known for its mechanical simplicity and reliability, but it's limited by regenerative heat losses, the turbine system proves even more effective. Stirling engines in this class commonly operate at 15 to 25%, constrained by cycle reversibility and thermal gradient limitations. This current turbine model nearly doubles that performance. This result validates simulation design choices, including fluid pathway geometry and torque extraction mechanisms, and positions the system as a highly competitive alternative to compact power generations or propulsion applications, which were thermal efficiency, where thermal efficiency is a critical driver. In conclusion, this turbine system demonstrates strong thermal and mechanical performance with an efficiency of 42.5% that far exceeds many conventional compact power systems like Stirling engines, Sproul, or turbines of the same size and capabilities. This design effectively translates thermal expansion fluids into mechanical work. The opportunity to further reduce losses through minimizing backflow or dead zones, optimizing wall heat transfer, investigating multi-stage or regenerative enhancements, advancing further hurricane energy extraction. Much like our own planetary environment, only one more controlled and less chaotic. The possibility of enhancement has been investigated and found to be highly possible through many different avenues. But the results that I have demonstrated here are not unrealistic according to Carnot or irreversibility, but possible as I have demonstrated and shown. Please analyze this seriously for yourself and come to your own conclusion. Written by Brian B. Williams, scientist, engineer.